Walls are an essential component of buildings, numerous and widely distributed within structures. Despite being relatively thin components, their safety and stability can have varying degrees of impact on buildings, especially when it comes to load-bearing walls. In real-life and practical engineering scenarios, there have indeed been numerous tragedies where structural damage and collapses have occurred due to wall failures. Today, let's learn together how to handle the detailed construction techniques of walls to ensure their excellent safety and stability. First, let's explore the characteristics of mixed structure walls. In mixed structures, walls serve as load-bearing components, and the weak points often lie in the mortar. In practical engineering, to enhance the seismic performance of walls, two measures are commonly adopted: height limitation and the installation of ring beams and structural columns. Height limitation ensures that, during an earthquake, the amplitude of sway of the building does not become excessively large, preventing walls from cracking and collapsing due to dislocation. Additionally, the installation of ring beams and structural columns forms an internal skeleton, reinforcing the overall height of the building. Now, let's delve into what exactly ring beams and structural columns are, their characteristics, and how they should be implemented. Next, we'll introduce these two components. Let's start with ring beams. As the name suggests, a ring beam implies a beam that forms a circle. In our engineering context, a ring beam refers to a continuous, enclosed beam installed along all exterior walls, or some interior walls at the roof and floor levels. From the definition of a ring beam, we can deduce several characteristics. First, ring beams are typically located at the roof and floor levels. They must be installed along exterior walls, and can optionally be installed along interior walls. Second, this type of beam is enclosed, meaning it must form a closed loop. When ring beams are installed in walls, they enhance the overall stiffness and integrity of the building, functioning like a waistband to prevent wall cracks caused by uneven foundation settlement, vibrational loads, and other factors, thereby improving the building's seismic resistance. To fully leverage the function of a ring beam, it should meet the following structural requirements. The ring beam should be continuously set at the same horizontal plane, and should form a closed loop. Second, the ring beams at the intersections of longitudinal and transverse walls should have reliable connections. Third, the width of the reinforced concrete ring beam should ideally be the same as the wall thickness. Fourth, if the wall thickness exceeds 240 millimeters, the width of the ring beam should not be less than 1/3 of its height. To further enhance the stability and seismic performance of walls, in addition to installing ring beams, it is sometimes necessary to install structural columns. So, what exactly are structural columns? Structural columns refer to small reinforced concrete pillars embedded within walls and arranged vertically along their height. The installation of structural columns can enhance the overall structural performance of a building, improve the wall's resistance to deformation, and ensure that the walls remain standing even after cracking due to seismic activity. Structural columns are generally set at the corners of buildings, at the junctions of interior and exterior walls, in stairwells and elevator shafts, as well as in the middle of some longer walls. These locations are not only crucial parts of the building, but also represent vulnerable areas in the structure. Second, the dimensions and reinforcement of structural columns. The minimum cross-section for structural columns can be 240 mm by 180 mm. For the longitudinal reinforcement, it is advisable to use 12 steel bars. The spacing of skirts should not exceed 250 mm. and they should be appropriately densified at the top and bottom ends of the column. In areas with a seismic intensity of 7 on the Richter scale where the building exceeds 6 stories. In areas with an intensity of 8 where it exceeds 5 stories. And in areas with an intensity of 9, the longitudinal reinforcement of structural columns should preferably be for no 12 steel bars, with stirrup spacing not exceeding 200 mm. For structural columns located at the four corners of the building, their cross-sections and reinforcement can be appropriately increased. The connection of structural columns. First, at the connection points between the structural columns and the walls. They should be built with zigzag joints, and two-tie bars should be installed every 500 mm along the wall height, with each end extending into the wall by no less than 1000 mm. Second, at the connection points between the structural columns and the rain beams. The longitudinal reinforcement of the structural columns should pass through the rain beams. To ensure that the longitudinal reinforcement of the structural columns is continuous from top to bottom. Third, structural columns do not need to have a separate foundation, but they should extend 500 mm below the outer ground surface, or be connected to a foundation rain beam with a burial depth of no less than 500 mm. From the introduction above, it's easy for us to think of another structure, which is the frame. In a frame structure, there are also beams and columns, known as frame beams and frame columns, respectively, similar to the principle of frame beams and frame columns. In mixed structures, rain beams and structural columns form a small frame to ensure the stability and seismic resistance of the structure. However, rain beams and structural columns are different. Their differences are outlined below. First, rain beams and structural columns are part of the wall and do not bear loads independently. Second, rain beams and structural columns are constructed simultaneously with the wall and are not infill walls. Third, the cross-sectional dimensions and reinforcement of rain beams and structural columns do not require separate calculations. Next, let's discuss the safety of infill walls. In framed structures, walls do not bear loads and only serve as partitions and for maintenance purposes. They are referred to as infill walls. It is important to avoid making them load-bearing components during design and construction. In engineering, a commonly adopted method is to lay bricks diagonally into the wall when reaching the last batch of bricks. During masonry construction, due to various needs, walls often have various openings, such as door and window holes, pipeline holes, etc. The creation of these openings can also have a significant impact on the safety and stability of the wall. Lastly, let's introduce the treatment methods for walls at these openings. For openings in masonry walls, the common treatment method is to install a lintel above the opening. Its function is to support the loads transmitted from above the opening and transfer these loads to the walls on both sides of the opening. Since bricks are interlocked when laid, an internal arching effect is created within the wall. Therefore, the lintel does not bear the entire load of the wall above it, but only a portion of it. Approximately the weight of the wall within a height range of 1/3 of the span of the opening. The common types of lintels include brick lintels, reinforced brick lintels, and reinforced concrete lintels. Now let's introduce them one by one. Brick arch lintels are a traditional practice in China, coming in two forms, flat arch and curved arch. Among them, flat arches are more commonly used in buildings. The overall performance of brick arch lintels is relatively poor, making them unsuitable for situations where there are concentrated loads above the lintel, or where the building is subject to vibratory loads. Currently, they are only used in simple structures. Reinforced brick lintels are formed by constructing a brick masonry and incorporating an appropriate amount of steel reinforcement in the mortar joints, due to their span of up to approximately 2 meters, and relatively simple construction. Reinforced brick lintels are currently widely used. The following are the structural requirements for reinforced brick lintels. Within a certain area above the opening, high-strength brick masonry should be used. The strength grade of the bricks should not be less than Mu 7.5, and the strength grade of the masonry mortar should not be less than M 2.5. The thickness of this part of the brick masonry should be more than 5 layers of bricks, and not less than 1/5 of the width of the opening. Steel reinforcement should be placed at the bottom of the brick masonry, with the two ends of the steel extending into the wall for 240 millimeters, and bent vertically for 60 millimeters to form hooks. The number of steel bars should not be less than 2. Reinforced concrete lintels have strong applicability, and are currently widely used in building construction. Based on different construction methods, reinforced concrete lintels are divided into two types: cast in situ and prefabricated. The cross-sectional dimensions and material configuration of reinforced concrete lintels should be determined through calculation, according to the upper load and the span of the lintel. The length of the lintel that extends into the wall on both ends should be more than 240 millimeters. To facilitate the masonry work of the walls on both ends of the lintel, the height of the reinforced concrete lintel should be compatible with the number of brick courses, such as 120, 180, or 240 millimeters. The width of the reinforced concrete lintel is usually the same as that of the wall, when the wall surface is not plastered. The width of the lintel should be 20 millimeters less than the wall thickness. In this lesson, we mainly discuss the structural methods to improve the stability and seismic performance of walls, focusing on the construction of ring beams, structural columns, and lintels. That's all for this lesson. Thank you.